Well, good morning, everybody. My name's Bill Brocklesby, and I'm from the University of Southampton. And what I'm going to do in the first talk this morning is tell you a little bit about using my What I'm going to do is tell you a little bit about the work we do at Southampton in High Harmonic Generation. First of all, I think a brief introduction for those of you who are not familiar with the geography so much. So Southampton is down here on the south coast of the UK, in the middle roughly. It's about an hour from London. And the university itself is a relatively modern university. It was started in the 50s, really. And it's something like 20,000 students. And it's particularly concentrates on science and engineering programs. So those departments are the largest within the university. It's right by the sea, so we have a strong marine presence as well. So we have a campus in the city, and we have a campus at the docks as well. So my research institute is called the Optoelectronics Research Centre. It's a department of the university, but it's a little out of the ordinary in that it doesn't have undergraduates. It's about 23 years old. It's about 170 people there working on areas of optoelectronics. There's a big effort in fibres and waveguides and telecommunications, which is the thing that the place has really been concentrating on. A lot about laser construction, and then application sensors and some sort of more fundamental photonics like metamaterials. We have a relatively new building. On account of doing this to our previous building, about 8 years ago, we managed to burn down the entire place. Not me personally, I understand. It was somebody else, I think. But the end result of that is that we now have a spectacularly nice new suite of labs and clean rooms that were funded on the insurance for the old building to the tune of about £100 million. And the facilities we have now are absolutely fabulous in terms of nanofabrication and things like this. It's something that we use a little bit in these projects, and you'll see some of the results. So we have all the facilities that you would need for fabrication of both optics and in nanotechnology, and it's an extremely nice facility to have, and it helps us a great deal in doing a lot of this work. So back to the topic in hand. What I'm going to do is just give you a brief introduction, brief motivation, but it's going to be really brief because you've heard so much about this stuff already. What I do want to introduce, though, is this idea of the time dependence, which is possibly something we haven't talked about so much this week. I'm going to go through a couple of simple models of high harmonic generation, an extremely simple one and a fairly simple one. And try and show you a lot of pictures along the way about how it works. Talk about how the frequency conversion works. Talk about what kind of a laser system you'd need to actually produce these pulses and why they're special. And then talk about how you try and generate XUV and X-rays efficiently using these kind of processes. I'll give you some examples of what these sources look like in the lab, the real parameters of what you can get from a particular source. And then I'll give you just a couple of examples. The first one is not my research, but I think it's particularly interesting, so I'll tell you about it, and that's attosecond pulses. And then at the very end, I'll tell you a little bit about XUV microscopy using these sources, which is my particular area of research. So, in terms of motivation, I don't need to tell you why that XUV is interesting. You've seen a lot of this stuff already. There's a couple of things that I'm going to talk about. There's the wavelength, which we've seen in great detail, allows you to do things like lithography, microscopy. So this is the roadmap that tells us we're going to do 13 nanometer lithography very soon, real soon now. And the other thing that, of course, is interesting is the fact that you can interact with these different shells, and you get things like the ability to do transmission microscopy in the water window, where you can aim between absorptions of oxygen and carbon. So, okay, we've heard about that stuff before. The other aspect that I want to talk about today, and the thing that high harmonic generation lets you get to, is astonishingly good time resolution. So we can generate pulses using high harmonic generation down into the tens of attoseconds. And just to give you an idea of that time scale, if you do a quick calculation of the electron orbit time in a Bohr model, it's about 150 attoseconds. So now you have laser pulses which are actually shorter than or as short in time as the electron motion within the atom. And you can do all sorts of things with those. I'll tell you about one application later on called the attosecond stream camera. But there's a huge number of applications just because of this time resolution, which you can only have when you get to the very high frequencies of the XUV radiation. So, soft X-rays, I don't have to tell you about soft X-ray sources. Pulse sources we've not concentrated on quite so much. For electron lasers and things like that, we heard a little bit about these yesterday. They have very nice properties in that they have very high brightness and pulses down into the femtosecond region, but not always what you'd call nice pulses in the femtosecond region. You saw the time behavior of some of the pulses from SASI FELs yesterday, and in the laser business, they wouldn't. Those kind of pulses would not be very popular. So, what do you get from high harmonic generation then? Well, the idea of this process is that what we're doing is a nonlinear optical frequency conversion, basically. So you may have come across second harmonic generation. The green laser pointers that everyone's been using earlier in the week use second harmonic generation. What high harmonic generation does is just an extreme version of that, exploiting the huge electric fields that we can get from these amplified femtosecond lasers. The laser systems that you require to produce this stuff are reasonably complex things and fragile things. But essentially what you need is millijoule level energies to a pulse, but in times less than 50 femtoseconds. And that's quite a rare laser. It's doable, but it's not easy. But what you get out of it from the pain of working with these lasers is an XUV beam, which is really very different from the kind of sources we've been talking about most of the week, in that you're producing a beam which is spatially coherent. It's very low divergence, milliradian level divergence, and in pulses of sub 10 femtoseconds, and can be produced at wavelengths sort of easily in the 40-50 nanometer regime, right down to below a nanometer, sort of a few kilovolts is the highest that people have got. So in the sort of soft X-ray regime, but it's the spatial coherence and this sort of much more laser-like beam, if you like, than many of the other sources that we've looked at that make it particularly useful for a lot of things. Just as a quick look at the properties overall of several of the systems for producing pulsed X-ray sources, they all have their good points and their bad points. The FEL sources are tremendous in that they have very high flux and tunability, and they can also have high spatial coherence, but the time structure of the pulses can be less than ideal, and also you have to sit around and wait a lot before you actually get onto one of them, and that would certainly drive me crazy. Laser-produced plasma sources we've heard about have some very nice properties. They can produce hard X-rays. You can actually have the source in your lab. You can work with them. But if you want spatial coherence, that's harder. If you want very short pulses, it's harder. And you have this property that you have to collect the light and refocus the whole time. The high harmonic generation, in comparison, the time structure is really very nice indeed and extremely controllable. Spatial coherence can be very high. The source can be produced in your own lab if you're willing to work with one of these fast lasers. The beam quality is very good, so we can focus these beams and work with them much more like laser beams. And this is actually an important point. There's an extremely good synchronization between the XUV and I say an 800 nanometer titanium sapphire laser pulse, which means that you can do pump probe experiments with good knowledge of the time. It's much harder for things like an FEL source to do the synchronization. So although that may seem trivial, it's actually very important experimentally. The bad points, because you know there must be some, the flux that you can produce with these things, nothing like as high as you'll get from an FEL source. And the wavelengths in general aren't as short. You can't really do hard X-rays at all. It's hard to get up even to a kilovolt with these sources. So you've got very soft X-rays and not that many of them, but the properties are very nice. And that makes it worthwhile looking at high harmonic generation as a source of X-rays rather than just an atomic physics experiment, I think. Yeah.
You mentioned that this laser plasma and high harmonic source are very liquid, so it is not the case in the free electron lasers, because
no.
You know that we submitted proposal 2 times, and 2 times was rejected. And if accepted, so we should wait 2 years for the beam time. So
Yes.
this is
Absolutely. This is my impatience here. I couldn't stand it. It would be driving me crazy.
We submitted application for a project related to nanoholography 2 years ago, but on this conference a week ago there was a talk on nanoholography at Flash.
There's also the small matter of the €1 billion that
we should be careful about it.
Oh, sure. No, I think it's a real benefit of these sources that you can actually get hold of them, and they don't cost €1 billion. And there's the Flash and Exfil have very unique properties, but not many people are going to get to play with them, so it's a problem. So, to start off with, I will do in about 3 slides the entirety of nonlinear optics. For those of you who are not familiar with nonlinear optics. Because in order to understand how you generate these high harmonics, you have to really look at the process. So if we go back to the very beginning of what we know about the response of an optical medium to light, what the incident light drives the electrons in the material, and you get the dipole moment because you're driving the electrons, and that dipole moment is proportional in some way to the electric field with constant here chi. That dipole re-radiates, and the interaction of this re-radiated wave with the wave that's transmitted gives you the effect of refractive index, and that's roughly what goes on. If we have that very simple model, then we can say that if we have small driving fields and the atomic response is just harmonic, then the re-radiated wave is just the same frequency, chi is just a constant, it's at the same frequency, and that's our sort of normal optics. If you increase the electric field, then chi isn't any longer a constant, and in fact it's proportional, varies with E. And in the case where the fields are not that large, you can make some kind of Taylor expansion of chi, and the dipole moment you produce is then given by this Taylor expansion. So, and that's the area of sort of perturbative nonlinear optics, if you like, where the field is a perturbation to the material. And in the very simple case, say if you've got a sine wave and you have a polarization of dipole that you're driving here is proportional to E and E squared, then you can just calculate that through, and if you substitute in this equation here for that with this P, what you see when you multiply all this stuff out is that you get a field at the frequency, a dipole moment at the frequency, a constant term, and a term at 2 omega. And so you get, if you start off with light at a micron, you end up with green light coming out, and that's the laser pointer. So the point about this is that it's the anharmonicity here that drives that 2 omega field. High harmonic generation is essentially an extreme example of exactly the same thing. It's a nonlinear optical process. But the difference here is that the electric field we're going to drive our atoms with is much larger than what this perturbative region. So you can't just do this expansion of chi to try and decide what frequencies you get out. You actually have to calculate what the response of the electron is in a much more detailed way. And I'll talk about some toy models of how you do that calculation later on. But it's you get this electron response, and you get it, which drives a dipole moment, which is and the drive is very nonlinear, and that's what produces these extremely high frequencies. And so what I want to do in the next 10 minutes or so is just go through some of the details of that. But I think it's important to realize that it's a nonlinear optical effect like this, and you can deal with it. And it has a lot of the same problems in terms of efficiency, because you're trying to get phase matching of the interaction. I'll talk about that later on. We can do a couple here of semi-classical models of what goes on, just to try and understand some of the parameters. The first one is the model that's really came from the very early days of high harmonic generation from Paul Corcoran, where we can try and get information about what goes on and some of the parameters of the high harmonic generation just by using, it's actually semi-classical in 2 ways, in that the light field is classical, and the light field will be classical in the other model that I'm going to talk about as well. So the atom, in this case, we start off by saying we can have tunneling, which is necessarily quantum mechanical. And then we're going to just make a classical model of the motion of the atom, of the electron that we're going to generate by tunneling in the electric field. and then we're going to have some other kind of quantum mechanical recombination. So the idea of this is that we can calculate things like the maximum energy that we can produce from a particular laser and a particular atom, and some of the phase shifts in the radiation we produce, and understand some of the properties of the radiation. So this thing is called the three-step model, and we can illustrate it with these pictures here. So the intention is that this sketch here is the laser electric field, so a single cycle. So in the case of 800 nanometers, about 2.7 femtoseconds from here to here. And this is our Coulomb potential. This is our electron wave packet inside the atom. So at the beginning of the cycle, this Coulomb potential is just in no field, and so it looks normal. If we wait for a quarter of a laser cycle, then the electric field of the laser is now of the same order of magnitude as the Coulomb field, and that means that the Coulomb field will be distorted. And so now we can draw our Coulomb field like this. So that's the extra field of the laser is added on to the Coulomb field. And that means that what was a potential well here becomes a potential barrier, and we can get tunneling out through here. And so the electron in here can tunnel out, and really the point, the intensity, the electric field gradient here at which high harmonic generation starts to work is the point at which the tunneling here has a significant probability over a time which is of order the cycle time of the laser. So we need to have a very narrow barrier here to hope that within this half cycle of the laser you get significant tunneling. If you do get tunneling, what you have now is an electron which, as soon as it gets a little bit away from the center of the Coulomb potential, is essentially almost in a free space. And we can work out the motion of that electron just using the classical equations of motion. So we're going to ignore, to work out the motion of the electron, we're just going to ignore this Coulomb potential entirely and say it's just an electron being driven by a laser field. What will happen then is that as the laser field cycles to zero, the electron is moving away from the atom, and then the electric field, due to the laser, reverses, and so we get a gradient the other way, and that pulls the electron back in to the atom core, and then you get this recombination event which emits an energetic photon. Now, the key things that we can get from this model is that the photon energy that we can produce here, the highest photon energy that we can produce in this recombination, is actually proportional to the kinetic energy of the electron as it crosses the ion core again. So as it comes back into the ion core, as it reaches x equals 0 there, it has a particular amount of kinetic energy, and it can dump all that kinetic energy as a photon. And that's the maximum amount of energy that you could get out. And we're going to calculate in just a sec what that will be just in a classical model of electron motion. It turns out that kinetic energy is proportional to the laser intensity. And so what we end up with is that the shortest wavelength that we can produce depends on the laser intensity, which from the point of view of the laser people is great, because that means if we crank up the laser intensity, we can get shorter and shorter wavelengths. And that's indeed what happens. So that's the key thing about high harmonic generation, which feels very different to second or third harmonic generation, is that the energy of the X-rays that you can get out depend as proportional to the laser intensity. What would we use ideally as a target for this? What atom should we put here? Well, what we'd quite like is that the field at which this tunneling occurs is as large as possible, because that field is going to determine how much acceleration we get and how much kinetic energy we get. So what we'd like here is something an atom with a very high ionization potential, because that means we can put on a very big field before it actually ionizes. And so what people tend to use most of the time are noble gases and helium in the end to get the very highest energies. So most of the experiments I'll talk about here are done with argon, because that's for the laser intensity that we have. That gives us about the right tunneling rates. The efficiency of the whole process, the recombination efficiency, decreases as you get up to these lighter atoms. So you'd kind of like to use heavier atoms, really. But they don't have the high ionization potential. So if you want the very highest energies, you have to use helium. And we can use molecular targets in here. And you actually get some very interesting information about the molecule itself from the way the electron tunnels out and recombines. And there's a whole field of very beautiful experiments trying to extract pictures of the electron wave functions from the high harmonic response, which is it's a very lovely piece of physics you can do with it. They're not so useful for using high harmonic generation as a source, just because they don't have the very high ionization energies that we'd like. So after this tunneling event, we've got an electron sitting in free space next to an atom with a velocity 0 and a position almost 0. We can just work out what it's going to do by using Newton's second law, classical, with the laser field in here as E. We can integrate that and get some answers, and we'll assume that the velocity as it tunnels out, its velocity and its position are pretty much 0 as the integration constants. And the key parameter which decides on what the electron will do is the time during the laser cycle when the tunneling occurs. So there's a picture here of what that looks like. And what I'm showing here is that this is the cycle of the laser. So that's, again, the period there is about 2.7 femtoseconds, so this is 800 nanometer light. It's one cycle of the laser. And looking at what happens if the electron tunnels out at different points within the cycle. And what happens to the trajectory is going to depend on what that tunneling time is. And what we're going to do is look at how the kinetic energy varies. We'll look at the kinetic energy in units of UP, this ponderomotive potential. UP is the amount of energy you can give to an electron if you just shine the laser field on it in free space. And that's what we use as our unit of kinetic energy, if you like, and it's proportional to intensity and the square of the wavelength. So looking in detail at this, if the electron tunnels out of the atom anywhere between the 0 of the field and the peak of the field here, then the trajectory it goes on never comes back to the atom core. So those electrons are lost, basically. They never recombine. And their trajectories just go off into the distance here. If you tunnel out at the peak here of the laser field, which is the most probable place and time you're going to tunnel, then the electron accelerates away, and then when the laser field gets to its maximum here, it starts to turn back again and reaches the iron core again at this time here. But you can see from this line here, so this line is the distance away from the atom against time, which means that the gradient of that is the velocity. So you can see here that when it reaches the atom core, the velocity is 0. It's actually just the point at which it stops and moves the other way again. So if the velocity is 0, then it has no kinetic energy, and there's no useful photons generated. So, but as you can see, this second point here is actually the red curve, and if it's born at this point here, then it's swept away. It starts to turn around slightly earlier, and now when it reaches the distance equals 0 line, which is where it hits the iron core again, the gradient at line is non-zero, and therefore you've got some kinetic energy. That means it's got a velocity, so it's got kinetic energy, and then you start to get energetic photons released. And it turns out that this the black line here, which is for an electron which tunnels out at about 0.3 of the period, that's 0.25, this is 0.3, and that's the maximum gradient at which the electron trajectory crosses the iron core, x equals 0 point. So the gradient starts off 0, it gets bigger and bigger and bigger to about there, and then for electrons which tunnel out later than that, the gradient gets lower again. So during this quarter cycle here, you get a variety of different possible trajectories, and then during this next quarter cycle, you get nothing again because the electron doesn't get back to the atom. And then during this quarter cycle here, you'll get electrons tunneling in the opposite, going the opposite direction because the field is reversed. And what we need to do is to look at what the energies are. We can have a look at that on this graph here. Now, what this graph here plots are two different things. I want to concentrate first of all on this green line. This is the time that the electron is ionized, so the time in units of this time of the period of the laser when the electron is ionized. And we said that about 0.3, this is the kinetic energy in units again of this ponderomotive potential. And at a time of about 0.3 period, then the kinetic energy is maximum. So this is when we'll get our maximum photon energy out, and that typically is, that's what people call the cut-off energy for high harmonics. That determines the maximum you're ever going to get out of it in terms of energy. And if you work through this calculation, it turns out that the maximum energy here is, well, it's, first of all, it's the ionization potential, because you get that energy back, plus about 3.2 times the ponderomotive potential. And I'll give you some real numbers for that in a little while so that you understand what energies we're talking about. But the important thing is that that's the maximum energy we're ever going to get. If we look at values of energy which are lower than this, then you'll see that if we're going to produce at 2 different times here, we're going to produce an electron which has kinetic energy of, say, twice the ponderomotive potential. And that becomes interesting later on, because that means we've got 2 different possible ways of producing the same energy, and when we do a slightly more quantum mechanical model, we're going to get interference there. And that's going to make the spectrum look reasonably complicated. This second curve here is the time that the electron spends away from the atom for each of these possible different energies. So that time is maximum for this electron that was born at the peak of the cycle, and then it gradually gets smaller and smaller and smaller as you go to later and later. I go back here. If we have an electron that's produced right there, very late in the cycle, it basically just goes like that and recombines very, very quickly. It has a very short trajectory. So that time it spends in the electron spends in the continuum gives you, in essence, a delay before it'll start radiating, and that changes the phase of the re-radiated wave later on, and that we have to take that into account when we're trying to make all the phases add up to get an efficient process. So people in the literature, if you read about this, people refer to these trajectories of the electrons born before the peak as the long trajectories, and these here as the short trajectories, even though actually it's a continuum. But that's what people, if you read long trajectory, short trajectory, that's what people mean, born before the peak or after the peak. And they have slightly different properties because they have a different phase of re-radiation. So if you want a picture of what's going on, it looks something like this. And there's a lot going on here, so I'll try and explain this. If this is the laser field, then what's happening is that every half cycle, we're going to get a delayed recollision event. And so what we'll end up with is bursts of emission separated by half a cycle. Now, that means that if we want them to, if we want the emission to add up, then it has to be a multiple. The only frequencies of all these bursts that will actually add up through the burst are the ones which are multiples of half a cycle, because the other ones will be out of phase. The emission here, if it isn't a multiple of half the cycle time compared to this one here, then the two will add up out of phase. So that means that what you get from the spectrum is that from these repeated pulses in time, essentially think of the Fourier transform of this, it produces a comb of frequencies, and this is the frequencies are separated by half the cycle time, i.e. they're twice the separation here is twice the frequency of the laser that you're using. And also, they're actually odd harmonics because each of these bursts has the opposite symmetry. One of them is from the field in this direction, the next one is from the field in that direction, so that means the odd ones add up rather than the even ones. So the spectrum produced is the odd harmonics up as far as the cutoff. This is in wavelength, and so the cutoff in this case is about here. And it turns out that below the cutoff, the spectral variation of these peaks is approximately flat, which is what people refer to as a plateau region. And so that's why you get a spectrum which are the harmonics. It's worth noting here that each of these individual bursts don't have this harmonic spectrum. You only get the harmonic spectrum when you add up the individual bursts. And we'll see that in a minute when we talk about attosecond pulses, because in an attosecond pulse you only keep one of these things, essentially. So that's what generates the high harmonic spectrum, and it gives you the odd harmonics of the laser because of this property that you have to add up the fields from all of these different bursts. So each of the bursts has a broad spectrum, and it's this intrapulse interference that actually produces the harmonic spectrum. It turns out that each of these bursts is also chirped because of this variation of the atomic phase the return time of the electron varies, and that gives you a delay, which translates into a phase shift. And that means that there's a phase shift versus frequency during the pulse, which is referred to as chirp. And we'll come back to that again in a minute as well. The individual bursts here are, for a typical experiment in argon at, say, 20-something nanometers, probably 300 or 400 attoseconds long. And you can almost think of this as in a similar way to a mode-dot laser, but maybe that's not useful at the moment. So, semi-classical, this Corkum model, the three-step model, has given us some useful information about, say, what the maximum energy we could produce is, and so forth. If we want to get a little bit more information out, we can make another toy model of what's going on by saying, we'll really now try and do some nonlinear optics. We'll try and calculate what the electron response will be. And if we calculate how the electron actually responds to the field, then we can look at the dipole we produce and then look at the spectrum slightly more accurately. So in order to do that, we'll try and generate the simplest model of the atom that we can that will give us the properties we want. So the model I'm going to show you pictures of here is a one-dimensional atom with a potential which is this thing called a soft Coulomb potential, where you take the Coulomb potential and add just a constant to it in order to make it, in order to stop it from doing anything unpleasant. The laser field here is always going to be classical still, so this is still a semi-classical model. So we can generate, so if we know the potential, we can generate a ground state wave function. That's pretty easy. And then we can take that ground state wave function and add a potential due to the electric field of the laser, and then just propagate this wave function in time according to time-dependent Schrodinger equation, and essentially just integrate that and see what happens to the electron as a function of time when we put this big laser field on. In this case, it's all done with numerical integration using this Crank-Nicholson scheme, but it's really the idea of this is that it's the simplest toy model that you can actually get some of this useful information from. And this is a picture of what goes on. So what I'm showing you here is actually what I'm plotting is the square of the wave function, or the mod squared of the wave function of the electron. And in this case, this is the distance away from the electron. Remember, it's just away from the core. It's a one-dimensional model. So if we go to very early times here, and then this direction is time, and it's in femtoseconds. I don't know if the scale's a bit small, but this whole scale is about 40 femtoseconds. When we go to times before the laser pulse arrive, this is just the ground state wave function of the electron within the potential well. So this is just a Gaussian-ish curve. And then as the laser field, which is shown in black here, starts to increase, and this is a 7 femtosecond laser pulse we're putting on here with a peak intensity. In this case, it was about 3 × 10⁻14 watts per centimeter squared. So when this laser field starts to increase, and nothing happens to start with, but you can see when the field gets to this value here, that delayed after the field, you can see some of the electron wave function being swept out of the ion core. So this is kind of the quantum mechanical version, if you like, of our Corkum pulling the electron away from the of the atom. We're not talking about tunneling of a particle over here, because that would not be appropriate. But what we're seeing is a bit of the wave function is pulled out of the core. And then again, you can just about see it swept back in again. And here it'll interact, and you can see that at every half cycle, and as the laser field gets bigger, it's larger and larger. Some of the wave function is pulled out of the core and then swept back in again as the laser field reverses. The reason the intensity, the wave function disappears out here is just that we're just cutting off the edges to stop any back reflections. It's just a numerical issue. So what's happening here is a bit of the electron density is going out of the away from the wave core, and the scale here is real. So this is nanometers. So in this case here, you're having electrons pulled 5 nanometers away from the atom, which is a very long distance in terms of the size of the wave function. The electron, and that's why this classical model works, is because you're such a long way away from the influence of the Coulomb potential. So the wave function is being swept out and then being swept back in again. And when it comes back in, what you get in this core region is the two of them, the bit that's left in the core and the bit that's been pulled out and swept back in, essentially interfere. and that changes the electron density very rapidly. And that's what drives that. So a change of electron density position is a dipole moment that's moving here. So that's what drives this re-radiated field, and that's what gives you the harmonic. So that's our dipole moment, if you like. We can look at the we can drag out the dipole moment directly from this just by looking at the expectation value of the acceleration of the electron at each time. And if we take that, if you could look very closely in here, what you'd see is that there's oscillations in the electron density in time, and that's what drives that's what produces the high harmonics. So this is just a summary of what's going on. You're having the electron dragged out of or bits of the electron dragged out of the core and interfering as it comes back in, and we calculate that by calculating the electron acceleration as a function of time. So this is a picture of at least the high frequency component of the electron acceleration as a function of time, which we can pull straight out of the quantum mechanical calculation. And you can see here that these are the bursts, if you like, that we were talking about in the very simple model. And then if we want to know what the spectrum of that looks like, then we can take the Fourier transform of the electron acceleration tells you the dipole moment. So if we Fourier transform that, we can get the spectrum. And if we do that, it looks like this. So this is a log of intensity versus energy here. And what we see is that up here, we see a cutoff. So that's good, because that squares then with the Corkum model, that there's some maximum energy that you give to the electrons above which you don't get any emission. So this is the cutoff, and you can see that near the cutoff, you get harmonics, these regularly spaced features in the energy, which are the harmonics of the laser. You can also see that down here, what you get looks like a mess. And the reason for that is because of this quantum mechanical interference that we talked about before. It's the fact that you've got many trajectories, different possible electron trajectories, contributing at each particular energy. And depending on the phase difference between those many trajectories, you get constructive or destructive interference. And it's quite a complicated pattern, and so you get what looks like irregular structure in here. But that's this quantum mechanical interference between trajectories. But up here you can see cutoff, and you can see the harmonics quite nicely at cutoff. So this toy model replicates reasonably well both what we see in experiment and also what we have from this.
So the cutoff, what it says that only the short or the long seconds are anticipated.
Well, at the cutoff, there's only one trajectory because that's the peak of this curve. So at the cutoff, yeah, you don't get the interference because it's only the only one that can happen. That's just an example of what happens if you go out to a 30 femtosecond pulse. You can see that this gets it's very complicated what goes on here, and that's the spectrum. The definition of the harmonics at the cutoff looks better, but again, it's incredibly complicated as you go into this plateau region. So that gives us a basic idea of what's going on, why the harmonics are produced. I wanted to zoom in a bit further and talk about attosecond pulses. You can only get these attosecond pulses in the XUV because of the frequency of what you need. And to some extent, as soon as you do high harmonic experiment, you already have attosecond pulses. You just have a train of them rather than a single pulse. Now, if you want to do an experiment with attosecond pulses and get the time resolution that's represented by the pulse, you'd like an isolated attosecond pulse, which is a bit harder. The simplest way of doing that is we know that the bursts of XUV are every half cycle, so if we could make the pulse short enough, we'd only get one. And that's the most straightforward way of trying to get this. We can also do things like mess with the polarization properties of the initial laser pulse, because it turns out that you only get harmonics for linear polarized light, because linear polarized light allows the electron to come back. Circular polarizes light, the electron misses the core when it comes back again. So if you can vary the polarization state through a longer pulse, you can get isolated attosecond pulses. But we're going to look at this one, the single cycle pulse. And just to flag up straight away, when you've got these very, very short pulses, there's another property of the laser pulse which we don't usually worry about for long pulses, called the carrier envelope phase, which becomes very important, and I'll talk about what that is in just a second. So a picture first of all, because it's nice and easy. This is the same calculation as before, this toy TDSE model, only in this case with a 3 femtosecond driving pulse. And what you see immediately is it's much simpler and that's because there are not so much interference going on, essentially, not so many different things interfering. And you can see that you get potentially sort of 3 or so bursts here. And the interesting thing about this is if you do the calculate the dipole acceleration again and take the Fourier transform to get the spectrum, you don't see the harmonic structure. And that's because, as we said at the very beginning, the harmonic structure only comes out from the interference between all the different bursts. So if you don't have many, many different timed bursts, then you don't get harmonic structure. And it's if we'd have started if the field had started by using 3 femtosecond laser pulses, it probably wouldn't have been called high harmonic generation, because the high harmonic generation only occurs because you've got long pulses. So if we'd have all had 3 femtosecond pulses to start with, it would have been called something entirely different, X-ray burst generation or something like that. And the harmonic structure only occurs when you make the pulse long. Here, you can see there's no harmonic structure. There's still some structure here, and that structure is, again, this interference between the different trajectories. So up at the cutoff, there's nothing, there's no structure. As you go lower in energy, here you've only got 2 possible trajectories interfering, and you can see that's a very nice regular structure now. And here you've got 3, so you get slightly more complicated structure. In an experiment, what you do to get attosecond pulses is take that frequency spectrum and filter out the top bit using some kind of spectral filter. Sometimes just you can get away with just using metallic filters. And if you do that, so if we filter out the structure at the bottom and then back Fourier transform into the time regime, you can see that, and this is numerically doing exactly that, you can see that essentially here we get a single burst of X-rays. And it's that was the first experiment done by Frank Krause's group. This is the original paper. This is 11 years ago now, so it's quite a while ago. And they managed to get a spectrum here, which gave them a pulse of about 500 attoseconds. This is from Nature from a long time ago. Now we're down to tens of attoseconds. This is last year's slide, so it says 80, but Mossy tells me that it's 40 now, is it? 40 something. As people get better and better at it. They're doing things like de-chirping the pulse by making all the different frequencies catch up with each other. So that gives us pulses down to tens of attoseconds that we can use controllably. But there's something we have to worry about with the lasers, which is we don't usually have to worry about here, and that's the fact that we can see pictures here. These are all excuse me. These are all 5 femtosecond laser pulses. But because what's changed here, they're all 5 femtoseconds. If you did the intensity profile of each of these, they would look identical. So if you took the mod squared of each of these, they would look identical. But they actually have a different phase relationship between the carrier wave and the envelope. And it turns out that for long pulses, this doesn't matter and happens all the time. That the phase between the carrier wave and the envelope and that shapes it varies as a function of time and position along the laser beam. It doesn't matter for anything above about 10 femtoseconds, but below 10 femtoseconds it does. They vary because the phase and group velocities are different for the laser, which we'd expect. If you think about what high harmonic would be produced by these pulses, well, this one, it may be that only this single central peak is big enough to actually give you tunneling, so that would give you a single attosecond burst. Whereas this one here has 2 peaks, which are certainly intended to be identical sizes. And so they might both give you tunneling. So that peak would produce you a single attosecond burst. That peak would produce you 2 attosecond bursts, even though they're both nominally 5 femtosecond pulses. So we have to worry about this carrier envelope phase, the phase shift between the 2 waves here. It turns out that carrier envelope phase is related to a problem in metrology, which is that if you look at the spectrum of our laser, so the lasers that produce this stuff are mode-lock lasers, so they have many frequency modes all running under a single gain curve. And a simple model would say that those frequency modes go down to 0, but in a real laser, there's a frequency shift here between the last mode and a frequency 0. And that frequency shift in the spectrum determines this carrier envelope phase. As that changes, the carrier moves underneath the envelope. And so in order to fix the carrier envelope phase, we have to know what this frequency shift would be. And measuring that was what got Ted Henschen's group the Nobel Prize, how many years ago? 3 years ago, was that? Something like that. So, and how it's done is very cute, so I wanted to tell you about how it's done. Essentially, what we do is produce a laser pulse which is wide enough in frequency space, so short enough in time, that the red end here is actually half the frequency of the blue end. So, just dropping back to that previous slide, what you got here was that the frequency of any of these modes could be written as the shift, omega naught, plus some integer number times the frequency difference between the modes. So what we want to do is find this shift. In order to do that, we can take this laser, which has a very, very broad spectrum. So this frequency is now double this one, so this is referred to as an octave spanning spectrum, an octave being double the frequency. If we take this laser mode here and ask what its frequency is, well, this one over here is, say, omega naught plus m times omega r. And what we're going to do is choose this one over here so that it's omega naught plus 2m times omega r. And these m's are just integers, so we can choose them. Each one of these modes has a particular value of m. And then if we take this one over here and frequency double it, so we filter it out using some kind of spectral filter, and then frequency double it, and the frequency of what we produce will be 2 omega 2, so that's 2 times omega naught plus 2 times m omega r. So now we've got a wave here which is omega naught plus 2m omega r, a wave here which is 2 omega naught plus 2m omega r. If we bring them together onto a photodiode, then what we'll see is the beat frequency between the two, the difference frequency. And you can see that if you subtract delta omega here is 2 omega 2 plus minus omega 1, which, if you work it out, is just our frequency shift. So by this taking f and 2f and interfering them together, we'll get the frequency shift. And that means we can know both the frequency shift and the frequency of the separation of the modes. We can know every frequency in this cone here extremely accurately. We can know our carrier envelope phase directly. And it also turns out that it means that you can use each of these frequencies in this comb as a marker to measure the frequency of any other laser. And so, although it seems strange, this is actually the most accurate way of measuring laser frequencies, even though it's a very, very short pulse laser. So that can fix our carrier envelope phase, and we can organize our laser so that we can set the carrier envelope phase to be what we want, and then we can get a controllable attosecond pulse. So, as is hinted at here, the lasers that you need to produce this kind of stuff are quite specialized. And so, I'm not going to talk in great detail about them, but I just want to show you a little bit about how you use them. First of all, what laser intensity do we actually need to produce this effect? Well, if we take that expression for the ponderomotive potential, and we know that the maximum cutoff is the ionizing potential plus 3.2 times the ponderomotive potential, then we can, putting that in real units, it's about IP. In EV, it's the ionization potential plus 3 × 10⁻³ lambda squared I, where lambda is in microns and I is in watts per centimeter squared. And if you calculate that through, so if you wanted to get 100 EV radiation and you were using helium as your ion, you could calculate that through, and the intensity you need is about 4⁻⁴ watts per square centimeter. And similarly, if you wanted to get up to 500 EV, we'd need 2.5⁻⁻15 watts per square centimeter, and those are very high intensities. They're not the sort of thing you find in a typical laser system. So what do you actually require to do HHG? We use a system where we can't get that much power, that much pulse energy out of an oscillator. So we have to use an amplification system, but you know from the fact that we're going to use these pulses to ionize atoms that the kind of peak intensities that we're ending up with are going to be large enough to damage a lot of materials. So you've got to be very, very careful how you amplify the pulse in order to try and not break the amplifier while you're producing these vast intensities. At the moment, what we need is a millijoule pulse at about 50 femtoseconds. That gets you to about 10 to the 14 watts per square centimetre without focusing too tightly. Just to give you an idea of how expensive they are, you can buy them now for about 300,000. They are actually getting cheaper. They've got cheaper by a factor of 2 in the last 5 years, probably. Whether they've got better or not, I'm not sure, but they're non-trivial lasers to keep running. So there's a certain amount of pain involved in doing that. What we're hoping is that we can replace these things with optical fiber-based laser systems. That's a whole other story. But the nice thing about them, and the key point to take away, I guess, is that you can do very high average power. And titanium sapphire lasers, which are the norm for this, produce nice pulses, but they don't produce very high average powers. In the ones that in people's labs typically are a watt or so, a few watts. Whereas with a fiber laser, we can do kilowatt average powers. That would mean more pulses. More pulses means your experiment happens quicker. So the use of fiber lasers, I'll show you a picture of one in a minute to do this, is potentially very nice, although technologically quite difficult. So how do you actually make the pulse when the intensity you want to end up with is big enough to damage the material? Well, what we do is use a system called chirp pulse amplification, where instead of we take a pulse from a laser oscillator, and then there's 3 stages to this. The first thing we do is put it through an optical setup which has dispersion in it. Dispersion being a variation in refractive index of wavelength, essentially. So what that does is, and you can use all sorts of things. You can use a block of glass, a pair of gratings. What that does is stretch the length of the pulse by speeding up the red components compared to the blue. So instead of our 30 femtosecond pulse out of the oscillator, we might stretch that to 300 picoseconds, so 10 to the 4 times longer, but now organized so that the red is at one end and the blue is at the other end. The good thing about that is if it's 10 to the 4 longer and the same energy, the peak intensity has just come down by 10 to the 4. So if we now take that pulse and put it into an amplifier, then we can amplify it up to the damage threshold of the material, and whatever that is. But it's actually still very long. And then what we have now is a second element, which is usually a pair of gratings, which reverses the effect of this original stretching and brings all the pulse components back together. So the only place you actually get the full pulse intensity is at the very end of that compressor. And then what you have to do is to engineer that compressor so that the very last bounce off the very last grating is slightly below the damage threshold of the grating. And you usually do that by expanding the beam. But everywhere else in the system, you're dealing with a very long pulse, which both doesn't damage the amplifier and also doesn't have particularly high nonlinear effects inside the amplifier. So this is chirp pulse amplification. Yeah. Yeah. Please.
Can you please explain the construction of this amplifier?
The amplifier is in principle, a very simple laser amplifier of exactly the kind. So it's in a block of material with an excited state population. The pulse comes in at one end, travels down the block, and as it does, you get stimulated emission, and that amplifies the pulse. So it's a bit more sophisticated than that when you do it, when you engineer it. But there's no extra science in there. That's essentially all the amplifier does. And the problem is, if you started with this very short pulse and amplified that, by the time you got halfway through the amplification, it would be so energetic that it would destroy the material. But if you make the intensity low by stretching it out, then amplify it, so you take the pulse, you chirp and stretch it, and then you amplify it, and then the peak intensity isn't too high, the final compression is what gives you the peak intensity.
Why do you stretch the pulse? Why not just have an input that's like already stretchable?
There's no problem with doing that. It's just that what you get out of a typical oscillator looks like that. The stretch in principle, I guess you could try and construct an oscillator that produces a stretch pulse.
I mean the bottom one.
So the sequence here is that you take an oscillator pulse, stretch it by chirping, amplify it up, and then you reverse the chirp.
Oh, yeah,
so which bit?
I'm wondering why you do. You get the first pulse. I mean, why not just produce a pulse like the second one?
It's just that most oscillators produce this. Simple oscillators produce that. In principle, you could construct an ample oscillator probably to produce a pulse like this.
All right, okay.
But the stretch factor here is extreme. It's much. The thing is that most oscillators require a short pulse to actually get the mode locking going.
Okay.
So, and actually this bit here is easy because in some systems all you do is stick it through a block of glass, make it travel this far through a block of glass, and that's done. So that bit's quite hard, that bit's extremely easy, that bit's moderately hard, and then this bit takes some thinking about because at the very end you've got the very, very high intensity. And typically in order to stop this final pulse from breaking the last thing it reflects on, you just make the beam big. And up to the very large sizes the old Vulcan compressor had the final gratings were 1 meter across. So the pulse was actually physically this big by that big by about, well, it had been about 20 microns. So this was a weird, very weird, physically a very huge sheet of light that was moving around. So that's chirp pulse amplification. This is what it looks like in a real system. This is a sort of block model of the one that we would use in the Southampton. An amplifier, an oscillator that produces the pulse at maybe a nanojoule, a stretcher, in this case 4 gratings, and then an amplifier where this amplifier works by letting the pulse in, bouncing it up and down about 10 times, and then kicking it back out again. But essentially it's just a laser amplifier, laser rod. And then here the compressor is used to bring the pulse back down again. That's all we need to know about that, really. And this is a similar thing made from fiber optics, which is something that my group in Southampton is interested in, where we're using fiber components for each of the things apart from the last compressor. So apart from that last compressor, which is physical bolt gratings, all of this other stuff is actually in fiber, which potentially has advantages in that it doesn't tend to go out of alignment and things like that. So it may be a very nice technology. The last thing we have to worry about here is how we actually build up the pulse through a piece of material, and that's this problem of phase matching. Essentially, what we're trying to do here is the same problem as we have in most nonlinear optics, and that's we're trying to get the build-up of the field as the wave propagates through the material to be coherent in that so that the field generated at each point by the nonlinear process adds up, because it's very easy to make it so that it doesn't add up. And this is important in second harmonic generation as much as it is in high harmonic generation. So a picture for second harmonic would look like this. If you've got, so the red wave is our fundamental, the blue is our harmonic, and you can see here that if the red and the blue are traveling exactly in step, then if we generate more light at B, then the light at B adds up in phase, the blue light at B adds up perfectly in phase with the blue light at A, and then we get addition. But it's quite easy that if the phase velocities of the red and the blue are not the same, we can easily see a point here where you generate blue light at A in the material, and by the time you get to point B, the blue light is actually pi out of phase, and so now the generated waves, the blue waves at A and B, would add up destructively and you'd see nothing. So if you don't get this process right, then you don't get any harmonic output, whether it's second harmonic or high harmonics. And the key thing here is matching the phase velocities, and so we get this synchronization. If you actually do a proper integral of the harmonic output along the length of a piece of crystal, so not just A and B but continuously, then if you get the phase matching right, and the phase matching here is essentially its momentum conservation, then if you get it right, you get this blue curve where the output increases with the square of the length. But if you get it wrong, then you get this green curve where the output starts to build up, and then gradually the second harmonic or whichever harmonic goes out of phase with the previously generated harmonic goes out of phase with the stuff you're generating now, and the output drops down to 0 again here. So we have to get this process right, get this conservation of momentum, in order to actually get any output. So if we had a crystal that was this long, and we tried to generate from it, or a gas jet that was that long, we would get nothing, even though there was quite a lot of intensity back here. So you have to get this bit right. And it's a question of matching phase velocities, and that's a problem because what we're doing here has got the two waves we're using have such different wavelengths. Now, if you've got red and blue, that's quite a difference in wavelength, and that's reasonably hard to match the phase velocities because the optical properties of the material change with wavelength. But now we're dealing with, say, 800 nanometers and 10 nanometers, and you know the properties of materials at 800 and 10 are very, very different. So matching phase velocities is very hard, just from the linear optical properties. And then you're also creating a plasma as you go, because part of the harmonic process is to eject electrons. So you're also creating a plasma, a time-dependent plasma. And you have this other phase shift that we talked about, where there's the delay between the electron being ejected and coming back again, which also adds a phase, which is intensity dependent to the process. So it's very complicated to get all of these three things to add up properly and give you a total delta K of 0. And it turns out that you usually need a fourth component to bring them back down to 0. And the two ways that we produce that are both geometrical. So we change the geometry of the experiment to give us a delta K of equal to 0. There's two very common ways. The first of all is to use something called the Gauss shift. Are you familiar with this thing called the Gauss shift? Anyone? Have you come across that before? Well, I'll tell you what it is. It's what you get is it's an extra pi phase shift of light as you go through a focus. Usually you'd never notice that, but it happens as you go through every focus. As you go through a focus, as you can see here, this blue light is supposed to be unfocused, and the red light is the focused version. They start there at the same frequency, but as you go through the focus, there's a shift of the red light, so that when you come out the other side, it's actually pi by 2, pi out of phase. And what that gives you is an effective change in the refractive index of the material. It's an effective delta K, and we can use that to match up and get our delta K equals 0. And the other thing we can do is use the waveguide dispersion of, say, this is a picture of a hollow capillary. And in this case, we're using the fact that the waveguide changes the propagation constants for the light. And we organize the waveguide such that the propagation constants give us this delta K equals 0. So there's gas jets where we focus through and use the Gauss shift, and there's capillary waveguides where we focus in and use the waveguide dispersion. Both of them can give us this effect of matching the phase matching the delta Ks and getting efficient generation. And this is what we get with the source at Southampton. We're using 38-ish femtosecond pulses, which give us 10 to the 14-ish watts per square centimetre when focused down to 100 microns or so. It's not a particularly tight focus. We can do this geometrical phase matching either via capillary waveguide that you've seen a picture of, or by using the Gauss shift, and we use both depending on which experiments we're doing. And these are the kind of output parameters. So we work typically between 18 and 40 nanometers because that's convenient for what we want to do. We're probably generating down to about 10 at the moment. The efficiency is low. This is 10 to the minus 5 efficiency, and that's good. That's as good as you can get, pretty much. Which means that if we put a watt of titanium sapphire light in, so these pulses are going at a kilohertz, we get about 10 microwatts of XUV out. It has the radiation has high spatial coherence, so that's very good for the experiment that we want to do. And the flux looks like about 10 to the 12 photons per second in something like a milliradian beam at about a 1% bandwidth, which in more synchrotron-like units is 2 10 to the 14 photons per second per square millimeter per square milliradian, and that's in about 1% bandwidth, which is it's not too bad really on the scale of things. It's certainly useful for experiment. The M squared, the beam quality is good before focusing, and it's about a 10 femtosecond pulse, and that gives us the what we need to do, the kind of experiments we do in Southampton that I'll tell you about later on. Yeah. Yeah.
What is the typical phase separation between typical cases? Would need to be matched to
The separation between the pump and the...
No, we need to it is matched, right?
Yes.
What's the typical phase difference?
Well, the phase difference, you have to aim to get a phase difference of 0.
Yes, but then the problem is...
As the well, what happens is as the phase difference gets bigger, then the distance. So the best you could do with a phase difference, in this case it's 4 radians, is a length of about this long. So there will be no point in doing your experiment in a material that's more than that long. So what happens is that as the phase difference gets worse, the effective length that you can generate over gets shorter and shorter. and so the signal you get gets smaller and smaller. So you have to aim to get, so if you have a gas jet that's 3 millimeters long, then you've got to aim, the most you can tolerate is a particular value of delta K, because if you go further than, if delta K is bigger than that, then you get no output. Does that make sense? So effectively, as your phase difference gets worse, the useful length of the generating material and the total intensity you can generate gets smaller and smaller. So you can work with all sorts of different values, but you just have to tune it to the experiment that you've got. So in this, if we had a gas jet that was this long, 0.3, whatever those units are, then we'd have to try and aim to get our phase difference less than 4 in order to get effective generation. So it varies depending on the geometry. So there's just some pictures of the lab. There's no people in the tool, so you get no scale, but that's there's the laser, and in this case there's 2 chambers, one vacuum chamber sitting over here that we use for beam characterization, and one over here that we do imaging in. And I'll show you some more of that later on. So the source properties are interesting because of the spatial coherence and these short pulses, but we have to live with low flux and complex lasers. But it does mean there are some experiments that are very useful. The spatial coherence has been demonstrated in some other by other folks. These are from the group in Colorado, showing you just overlapping interference between shining our beam onto 2 apertures and looking at the interference, and you can see that the contrast on these fringes is really pretty good. So we do have spatial coherence. Temporal coherence isn't that high because it's a very short pulse, but the spatial coherence is extremely good. There are many applications that people have worked on. Attosecond physics, molecular imaging, surface physics. You can just use these as sources for spectroscopy. You can seed other X-ray sources, and we heard a little bit already about seeding of FELs and X-ray lasers with harmonics. You can do imaging, holography, many others. The 2 I'm going to talk about briefly are the attosecond street camera and imaging, which is my particular area of research. But first of all, attosecond street camera. This is all from Ferenc Krause's group at Max Planck and Garching. And one of the interesting things here is that what we're going to use this attosecond pulse for is actually to measure the electric field, in this case of the laser, directly, point by point, through the cycle. And the way this is done is to take a femtosecond pulse here, generate some harmonics, and generating them in this case in a gas jet, so using the Gauss shifter phase match, in neon gas. What you get out is you get the rest of the laser, the red beam, and you also get a harmonic beam. And what this group do is shine that onto a mirror, which is in 2 sections. You can see there's an inner section to that mirror. And it turns out, as you'd expect, that the XUV divergence is much smaller than the red beam. So effectively, this outer part of the mirror reflects the red beam of the pump laser. The inner part of the mirror here reflects just the XUV. So now, if we move the 2 of them with respect to each other, we can move the timing of the pump laser with the XUV pulse. And that's what this experiment does. They focus down onto another gas jet, basically, and do some photoionization. So you're photoionizing with an XUV pulse in the presence of a laser field. And in this case, they're using up to about 100 eV. And what they see, the kind of thing, so what you're doing is bringing an XUV pulse at the same time as a laser field and photoionizing with this pulse. And it turns out that what you do, what happens is that the field of the laser changes the energy of the photoelectron that you knock out, because instead of photoionizing in zero field, you're photoionizing in the laser field. And so by moving the ionizing pulse with respect to the laser field, because the ionizing pulse is very short, then you can actually, by looking at the variation in the photoelectron energy, you can actually map out the field of the laser. And that's what this picture is here. This is photoelectron kinetic energy. And you can see that as they slide the delay here, so this is delay in femtoseconds. So femtoseconds is about 300 microns, so they're moving this mirror, 300 nanometers. So you're moving this mirror with a few nanometer accuracy. But as you do that, you can see you actually track out and measure, if you like, the field of the laser point by point. And it's that ability to do pump probe experiments where on this time scale that's accurate to a few attoseconds that people are very excited about, and that's what people are using to do. Once you can do this, you can do all sorts of other experiments in the same idea. So this is the attosecond street camera, which is one of the very earliest experiments that people did, effective experiments with single attosecond pulses. This was actually done, again, by Krause's group in about